Hello. So in this video, we're going to continue studying properties of congruences. And one property that is very important is cancellation. So if you remember, here's the definition of congruence, and here's the properties that we've proved so far, and we've seen several examples of why those are very useful. But one property in particular is this property, that if A and B are congruent, then multiples of A and B are also congruent. So if A and B are congruent, then K times A and K times B are also congruent. And the question is whether this is an if and only if. If you have a multiple here, what we would like is to cancel the case and get that A is congruent to B modulo M. So let me show you some examples and see if that actually works. So is this true? So if I have a congruence, for example, 16 is congruent to 6 modulo 5. Is that true? Yes, because 16 minus 6 is 10. 16 minus 6 is 10, which is a multiple of 5. So that is true. And 16 is 2 times 8, and 6 is 2 times 3 modulo 5. So can I cancel those, the 2 here and the 2 here, and get a true congruence? Does that imply that 8 is congruent to 3 modulo 5? Yes, that is also true, because 8 minus 3 is 5, right? Not congruent, equal. 8 minus 3 is 5, which is divisible by 5. So that congruence is true. However, let me write it big and red here, angry red. However, this doesn't always work. So for example, I can have, let's see, 15 is congruent to 21 modulo 6. Is that true? Sure, 15 minus 21, that is minus 6, which is 6 times minus 1, so it is a multiple of 6, so that is a true congruence. 15 is 3 times 5, and 21 is 3 times 7. That is true. However, this does not imply that I can cancel these 3's and get that 5 is congruent to 7 modulo 6, because that is not true. This is not true, right? Because 5 minus 7 is minus 2, which is not a multiple of 6. So that's annoying. That's annoying because in the integers, so in the dreamland of the integers, we do have that property, right? If A times B is equal to A times C, and A is not 0, then B is equal to C, right? With in the integers, this happens. There is cancellation. So what happens here is that I can cancel these A's and get that B is equal to C. But this doesn't seem to be true in some cases. And what is the culprit here? The culprit is that, well, here 2 is actually relatively prime to 5, but 3 is not relatively prime to the modulus. So that's why I'm not going to be able to cancel that 3 in general. So let me show you then what is actually true. So here's the statement that we're going to prove. Let A, B, and K be integers, and M and N be bigger than 1. Then first, if A is congruent to B modulo M, and D is a divisor of M, then what is true is that A is congruent to B modulo D. Okay, so if D is a divisor of the modulus, then I can reduce also and get a true congruence modulo D. Okay, we'll see examples of this in a second. And 2, if K times A is congruent to K times B, this is the case where I would like to cancel the K, then what is true is that A is congruent to B modulo M divided by the GCD of K and M. So in particular, if K A is congruent to KB modulo Kn, then yes, then I can cancel the K, but also in the modulus. So A is congruent to B modulo N. And if Ka is congruent to Kb modulo M, and the GCD of K and M is 1, then I do get that A and B are congruent modulo M. Okay, those are just applications of that formula up there. So let me prove these formulas. Let me prove what's happening here, and then we'll see some examples. So first of all, let's prove part 1 first. So suppose that A and B are congruent modulo M, and suppose D is a divisor of M. Okay, and D is bigger than 1. Then I can write M. D is a divisor, so there is going to be a D and an M prime such that this happens for some integer M prime. And then, or let me just, okay, so yeah, M is D times M prime for some integer M prime. Then what happens? Then A minus B, M minus B is a multiple of M, so it's M times K for some K. And then I can rewrite M as D times M prime times K, and I can rewrite this as D times M prime times K. So D also divides A minus B, which implies that A is congruent to B modulo D. Okay, that proves part 1 of this theorem. Let me just do perhaps a quick example here in that, let me, just one quick example here would be that if, let's say, so 8 is congruent to 2 modulo 6, right? This is true because 8 minus 2 is 6. Then this also implies that 8 is congruent to 2 modulo any divisor of 6. So this is also true modulo 3, because 8 minus 2 is 6, which is 3 times 2. And 8 is congruent to 2 modulo 2, which is true because 8 minus 2 is 6, is 2 times 3. Okay, so that's what it's saying. All right, let's then prove part 2 of the theorem. So we want to prove, let me lasso this here. This is a statement. This is what I want to prove. Okay, so this is the statement that we want to prove is this. And this is a proof of that fact. All right, so let's prove this. So if Ka is congruent to Kb modulo M, so K times A is congruent to K times B modulo M, that implies that, well, there is some age such that KB, or yeah, KB minus KA is H times M. And this KB minus KA, this can be written as K times B minus A, is H times M. Okay, now suppose let's call the GCD of K and M, I'm going to call it G. Okay, then G is a divisor of K and a divisor of M, so let's write K as G times K prime and M as G times M prime. Then this equation, let's call this a star. The star now implies that I can substitute these G's and K's in there. So I can write G times K prime times B minus A is the same as H times G times M prime. And I can cancel, this is in the integers, so I can clear these G's to get that K prime B minus A is equal to H times M prime. Okay. So this implies that M prime divides K prime times B minus A. And now, since K prime and M prime are actually relatively prime, so this was an exercise. This was actually exercise. This is exercise 2.1125 in the book. What this says is that the GCD of K over G and M over G is 1, where G is the GCD of K and M. So that tells me that the GCD of K prime and M prime is 1. But you see, we have two conditions here that are familiar. M prime divides this product, and M prime and K prime are relatively prime. Those are the conditions for our favorite corollary for Euclid's lemma to prove that an M prime has to divide B minus A. So now by Euclid's lemma, that implies that that M prime actually divides B minus A, and what that says is that A is congruent to B modulo M prime. Okay, but what is M prime? M prime is M divided by G, so A is congruent to be modulo M over G, and G is the GCD of K and M, which is what we wanted to prove. Okay, and those other properties just follow directly from this formula. All right. So let me show you how to use this. So for example, I've already shown you one example of the first property. So for example, 29 is congruent to 44 modulo 15. This implies, since 15 is 3 times 5, this gives you congruences modulo 3. And also it gives you a congruence modulo 5. Okay, so those are true. You can check that these are actually true modulo 3 and modulo 5, as well as modulo 15. But what about the other property, which is, what can I say about cancellations? So for example, I have that 3 times 5 is congruent to 3 times 7 modulo 6. That's what we saw. But it is not true that, so 3, that I can cancel that 3. So 5 is not congruent to 7 modulo 6, so I cannot conclude that. Okay, but what can I conclude? What I can conclude is that what is true is that 5 will be congruent to 7 modulo 6 divided by what I'm canceling by, the GCD of 3 and the modulus. So the best I can say is that 5 is congruent to 7 modulo the GCD of 3 and 6 is 3, so this is 2. And that is true. 5 and 7 are congruent to 7 is 5 and 7. 5 minus 7 is minus 2, which is 2 times minus 1. So this is true. So you cannot just cancel the 3 in here because there is a GCD. The GCD is non-trivial with 6. So canceling, you have to be careful with the possible GCD. So I can't conclude this, but I can conclude this much. And that is true in this case. Okay. One important consequence of this will be the following. Suppose that P is prime, and suppose that I have any congruence, K times A is congruent to K times B modulo P, and K is not a multiple of P, with K with P does not divide K. Automatically, that tells you that the GCD of P and K must be 1, because the only possible divisors of P are 1 and P. So then by our theorem, what we just proved, that will say that A is congruent to B modulo P divided by the GCD of P and K, which is 1. So that will say that A and B are congruent modulo P. So with a prime moduli, if the modulus is a prime number and K is some number that is not a multiple, K is some number that is not a multiple of P. Otherwise, if it's a multiple of P, this actually is multiplying by 0. So it would just read 0 equals 0. So if this is not a multiple of P, then I can actually cancel the K and don't worry about the modulus. It will not change. So that will be helpful when we talk about congruence classes modulo primes. It will be easy to do cancellation on both sides. Okay, so I'll stop here. And next, we're going to talk about some application of congruences to divisibility tests.